Yesterday we raised the question about what we may call as a diagonalization of a matrix. For instance, I pointed out that you could think of generally a linear transformation which, let's say, from an n-dimensional space to another n-dimensional space, so the matrix representation of the operator will be an n by n matrix in a particular coordinate system that we may choose for V. So the representing the coordinate system I choose, for instance, is this, right? And the matrix representation I can call as A, and if it is a different one, then we call it as A bar, right? So now the relation between A bar and A can be represented by means of an invertible n by n matrix, which we may denote by P. Represents the transformation matrix corresponding to the two sets of basis vectors. So it will involve obviously dot products of the basis vectors in the one set with respect to those in the other. So I'm not going to write down the formula for PI, but this is the one. So you can ask, instead taking this as our basis set, I can ask if through a transformation, right, I can get to this such that P inverse AP or A bar is actually equal to a diagonal matrix. Right? Is it a diagonal matrix? I can ask, does there exist such transformation of coordinates so that the representation of the operator actually becomes diagonal. That means it has only the diagonal elements and no other elements. All the off diagonal elements are zero. Right? So now for any arbitrary transformation of matrix, for instance, let us say to get to A, this will be our base matrix. From there I am going to transform. Right? Now what properties should A have so that this is possible? Does all matrices have a diagonal representation or not? Not necessarily that invertible matrices have to have a diagonal representation. Distinct eigenvalues, that is one. So fine. But if the eigenvalues are not distinct, can it still have a diagonal representation? Because my requirement is it should have a diagonal representation. Not all the eigenvalues have to be equal. Yes.
Independent eigenvectors.
Independent. It's not an orthogonal matrix. Yes. Symmetric matrix, definitely. A symmetric matrix has the property. Of course, you can ask, the symmetricity doesn't depend on the basis, right? But I think you can show that if you are restricting yourself to orthonormal basis sets, then symmetricity is preserved as you transform from one to another. There are somewhat intricate theorems that depend on certain properties of the basis sets, but in general, let us assume that A is symmetric, right? That means in one representation it is symmetric. Then you can show that the eigenvalues first will all be real, right? So symmetric matrix will have real eigenvalues, and further, right, the geometric multiplicity will be equal to the algebraic multiplicity, because that is what we want. Of course, if you have this, the geometric multiplicity cannot exceed the algebraic multiplicity. Algebraic multiplicity is how many, to what extent a particular lambda I, let us say, is repeated. So let's say lambda I is a double to a particular eigenvalue, then its algebraic multiplicity is 2. Our geometric multiplicity cannot exceed 2, but it can be less than 2. It has to be at least 1. Right? So algebraic multiplicity of lambda I, let's say, is 2. geometric multiplicity is less than or equal to 2. These are basic theorems, and in fact it has to be or we can say that this is less than or equal to a lambda I. So I don't even have to consider 2. Right? In general, geometric multiplicity has to be 1, right? Because once you have an eigenvalue, it has to have an eigenvector, right? So that is a geometric number of eigenvectors, linearly independent eigenvectors corresponding to a given eigenvalue. That is a geometric multiplicity. It has to be 1, right? And it also cannot be greater than the algebraic multiplicity. But for instance, if G lambda I is less than A lambda I, right? Even for one eigenvalue, the geometric multiplicity is less than the algebraic multiplicity, then we will not have a diagonal representation. The criterion is not, of course, that will automatically be satisfied if the algebraic multiplicity of all the eigenvalues is 1. That means all the eigenvalues are distinct, means geometric multiplicity minimum has to be 1, maximum is also 1, so geometric multiplicity will automatically be 1. You will get as many eigenvectors as corresponding to the dimension of the vector space itself. Then the eigenvectors will form a basis set, and in that basis P inverse AP would be diagonal. So in that case, P would actually be the matrix of eigenvectors. It's very easy to show. Then you have an exactly diagonal representation, right? So, but certainly, if the matrix is symmetric, even if the algebraic multiplicity may be 0, the algebraic multiplicity may be greater than 1. That means the eigenvalue will be repeated. So there is no requirement that all the eigenvalues will be distinct. But for symmetric matrices, it is possible to show that the geometric multiplicity is equal to the algebraic multiplicity for all lambda I. So if that means a particular eigenvalue is repeated twice, then it will have 2 linearly independent eigenvectors corresponding to it. So symmetric, if the matrix is symmetric, right, then there certainly exists a basis set, right, in which the representation of the operator would be diagonal. Right? So in the same way now, we know that the deformation tensor is symmetric, and so is the stress tensor. So both of them will have a diagonal representation. I'm not going to give an outline of the proof. Now D is f of D. Now we know that both are diagonal. So D is the symmetric part, and so both are symmetric, not diagonal. Both are symmetric. D is the symmetric part of the velocity gradient tensor. Stress, by the angular momentum principle, we have proved that the stress tensor is symmetric under certain restrictions, and those restrictions are the only ones Stokes considered. Right? So by the angular momentum balance, both are actually symmetric. So let us say that under a particular transformation, right, which now here I will consider only orthogonal transformation, so we don't have to worry about the complications arising over non-orthonormality of the basis sets. We consider only those, right? So certainly there exists a matrix, certain transformation exists. So if I transform it to D bar, then that would be definitely diagonal. This would be the form of D. So I consider that transformation. This is actually what is called as the principal axis of deformation. That is the coordinate axis or coordinate transformation that makes the deformation tensor diagonal. That is called as the principal axis of deformation. So to transform it, and it is certainly possible that there exists at least one transformation in which the deformation tensor would be diagonal. Now what can you say? So I make the same transformation for T, right? And so that need not necessarily be diagonal. There is no requirement that that is diagonal. However, it is possible. So let us say that this is this is one transformation which makes D diagonal. Then the D would have, let's say, the following form. on the face of it, there's no requirement. T also will have one coordinate transformation which will make it diagonal, right? However, it is possible to prove, and that is what is proved in Aris and Seri, it's possible to prove that the same transformation that which makes T diagonal would also make T diagonal, right? So it is possible to prove diagonal. We can give you a proof of it. Proof is fairly straightforward. You just follow Aris. So it's possible to prove that under the same transformation, let's say some transformation L, right, makes this like this. So D is converted to, that means L transpose D. L is D bar, it is diagonal, let's say. Then the same L, that is the same coordinate transformation, is possible to prove that T would also be diagonal and it will have the, that is a very crucial thing. Because both T and T are symmetric, we know there exists one coordinate transformation for T which would make T diagonal. There exists one coordinate transformation which would make D diagonal. This is a very important result, right? That will prove that the same coordinate transformation which will make D diagonal will also make T diagonal. It's very straightforward to prove. Somewhat technical, I am not going to go into it. It's easy for you if you follow Aris or Seri, you can definitely get it. Those are known as the principal axis. So the principal axis for the stress tensor will also be the principal axis for the deformation tensor. Having proved it, right, now I'll give a simpler proof for the Stokes' final result. For mainly the case where we assume on top of the three hypotheses of Stokes, we assume a further restriction that the relation between T and D has to be linear. Right? In that case, I'll give a proof. The ideas used in that proof will also be applicable to the more general case, okay? Because we pointed out this will be the first step in either case. It's the general case which will lead to E equal to alpha I plus, or the special case where T in addition is linear in D. So both the cases, this is a very important first step to show the same set of coordinate transformation that would make D diagonal will also make D diagonal, and you can see why this is important. First of all, the fact that D and D both have a coordinate transformation that will make them diagonal is ensured by the fact that both of them are symmetric. The important thing is that the same transformation that would make D diagonal would make D diagonal. Then I can look at that particular coordinate transformation. The proof will become easier both in the general case and in the special case, right? Because when you are dealing with the general case here, under an arbitrary set of coordinates where all the 9 elements are present, we are looking at a relation between the 9 elements of T on the one hand and the 9 elements of D on the other. Here I have to deal with only 3 elements of T on the left hand side and 3 elements of D on the right hand side. So that would clearly be simpler to treat. Yes?
Sir, L is composed of the matrix of the column is eigenvectors.
No. We are not talking about, let's not get it here. It might be, but I am not going to go into that. Right? Fact is that there exists a transformation that would make D diagonal. That is ensured by the symmetricity of the. I am not going to say each and every theorem in linear algebra here. I am only using those that are relevant in this case. All I need to know is that there exists a transformation which would make D diagonal. That is ensured by the symmetricity of the D. Right? Whatever coordinate system you use, D is symmetric. That is not dependent on which coordinate system you use. Right? Same way, the symmetricity of T is independent of any coordinate system that we choose. Right? Because that is the inherent property of the stress and the deformation tensor. So automatically the theorem in linear matrix algebra says that there exists a transformation which will make D diagonal. I would say exists a transformation which will make T diagonal. What you have to prove that the same transformation which makes D diagonal will also make T diagonal. That is very important. That will be important for our proof because I am not going to consider that particular coordinate system. I don't care whether it is composed of eigenvectors or what right now, right? But I am going to look at that. Now I am going to prove that assuming the linearity, what form the relationship between E and D would be. Because the important point here is that the second hypothesis of Stokes says that so if I am able to establish a relationship in one coordinate system between E and D, the same form will hold for any coordinate system. Obviously, in any case, we want to look at both T and D, evaluate its components under one coordinate system. I cannot choose one coordinate system for T and one coordinate system for D. And that is absurd, and that's meaningless. So once I have chosen a coordinate system, D will have certain components, D will have certain components. Now, what the Stokes' second hypothesis says is that whatever the coordinate system I choose, the function that determines the relationship between the components of T on one hand and those of D on the other will be the same. So, if I can find out what that function is in one coordinate system, I know its functional form in any coordinate system, and clearly this being composed of only 3 elements each will be the easiest to work with. Right? So, the linearity implies, I'm now following almost identically the steps in Seguin and Aris, so the notation would be the same. So I will have the linear, now I am proposing that the linear relationship between T and D, components of T and the components of D, and the linear relation will have T1 equal to A1 D1 plus A2 D2 plus A3 D3. Plus I am also going to make it the fourth hypothesis or the third hypothesis that T should be equal to minus P times I, right, when D is 0. So this would be the most general form that would take it upon both the linearity and that, right. So T2 is, I will make it P1 D1 the trick in most of these proofs depends on choosing particular orthogonal transformation and making a transformation that makes our proof easier to implement. So what Seguin does is, let's say I consider one transformation L. Right now from the diagonal I am going to transform. I have already reached the diagonal and I am saying that because it's linear it has to have this form. So we are not attempting to give the more general case when you get the d squared term also. Right? So I am restricting myself to the simpler case. And what about A1, A2, A3? They all have to be constants here. They cannot be dependent on D because of the linearity. So that's why it's easier to give that proof here. But L considers now 0, 0, 1, 1, 0, 0, 0, 1, 0, a particular L. Right? Now first you have to verify this has to be an orthogonal transformation because that is all we are considering. Right? How do you prove that this is orthogonal? What is the criterion for orthogonal? L transpose is equal to L inverse. Now does this satisfy that criterion? How do you go about proving it? One is to calculate L inverse. What would be the other? You just have to verify. Multiply. If I multiply L transpose L, and if I get I, right, it implies that L transpose, that's very easy to do. I don't have to calculate the inverse. Right? Transpose is very easy to make, but this is going to be also probably is it a symmetric? No, it's not a symmetric. So it is this. So the net effect of this on D would be what Seguin calls a cyclic permutation. What this would do, if I now act this on D, right? So I have 0, 0, 1. L transpose I have to take. Right? L transpose would be 0, 1, 0. This would be 0, 0, 1. The first row becomes the first column. The second row becomes the second column. The third row becomes the third column. Right? So that's correct?
Yes. Yes, sir.
That is M transpose. Right? So because there are so many zeros, I think it's a bit difficult to find the transpose. So it's a bit confusing. And then I put the original L matrix. This is what I have to do. This is the transformation I am considering. Right? 1, 0, 0. And 0, 1, 0. Now you can easily verify that this could lead to the matrix B2, B3, B1, which is why it will continue to remain diagonal, right? But this is why he calls this a cyclic permutation matrix, because D1 has now become D2, right? Wherever D1 was, now I have D2. D2's position has been taken by D3, and D3's position has been taken by D1. So you can expect when you operate this on T, the same thing would happen. T1's position would be taken by T2, T2's position would be taken by T3, and T3's position would be taken by T1. So now I get T1, wherever T1 is there, I have to write T2. This is what the meaning of this is. That's why I am doing this too, so that you understand what we mean by orthogonal transformation and how it is actually acting on D1, D2, and D3, and D1, D2, and D3. So this will be T2 equal to, wherever I have D1, I have to put D2. So it's not going to be the same equations. That's why we get something out of it. A2, D3 plus A3, D1 minus B. When D3 and B, there's no change in that. Now T2 will become, the same thing will happen to T1 will become T2, T2 will become T3, and T3 will become T1. So the next equation, right, would be T3 is equal to V1 D2 plus V2 D3 plus V3 D1 minus B, and similarly the third equation will become T1 is equal to C1 D2 plus C2 D3 plus C3 D1 minus B. So let's now compare T1 here on the one hand and T2 on the other. Right? So what Serin concludes is that if you compare the coefficients, obviously we are assuming neither D1, D2 or D3 are 0. Otherwise this proof might become more complicated. I don't know whether you can actually need to assume that. Certainly not all of them can be 0. It's certainly possible that one of them can be 0. But anyway, the proof that I saw that effectively assumes that D1, D2 and D3 are not 0. So let's take that, right, as given. Now you will clearly see that what you will get is that I have to equate the coefficients of D1. I get A1 equal to C3, right? And then A2 is equal to C1, and A3 is equal to C2. Right? Now if I compare the coefficients of T2 and T2 here and T2 there, right? B1, right? What is B1 equal to? A3, right? B2 is equal to A1, and B2 and B2 and B2. So B3 is equal to A2. You have to ensure that I have written it correctly, because I am a bit confused as to these indices, but I think I've seen it correctly. B3 is equal to A2. Yeah, that seems to be correct. We have more here because A1 equal to C3 and it's also equal to B2. So A1 equal to C3 equal to B2. So I can combine, right? B1 equal to A3 equal to C2. We get more relations, and B3 is equal to A2 is equal to C1. And you can also compare now the one that is D3 only compare, but if you convince yourself you won't get any new results, right? But this is not all we can get. What then considers is another transformation. So we will consider another transformation acting on the original D1, D2, D3, right? So you consider another transformation. L is now equal to 0, 1, 0, 1, 0, 0, 0, 0, 1. Right? This also you can verify as an orthogonal transformation, and what it will give is under this transformation D1, D2, D3 is again on the original equation will transform, not equal, will transform to D2. So D3 is not transferred, D1 and D2 are just exchanged. So the meaning of this is that if this acts on, this is not multiplying, you have to take L transpose DL. So this is effectively means D1 and D2 get interchanged and D3 remains the same. If you do that, then what you will get are a set of additional relations between the coefficients. I am not going to write that down. I write the final answer. So you can see roughly the way the whole proof proceeds. Right? So first you establish that both T and D have the diagonal representation under the same path. That proof also depends on some kinds of transformations like this. You can go and follow Aris or say, right? Very similar type of arguments. So you establish that. So you say that restricting our proof to the case where T and D are linear, I say that this is the most general form of linear relation between the components of T and D, and then I apply further orthogonal transformations and use the fact that D transforms in one way, D will transform in the same way, and then of course you can argue by trying some other transformations, you will get some other results. Probably not, or obviously not, right? These are probably the only set of relations you get, because these transformations are, you can consider some other orthogonal transformation and try some other set. Here he has considered 2 and he has exhausted all possible relations you can get. Now the question is, if I use some other set of orthogonal transformation, will I get something different? And my guess is probably not. Right? If you prove that you get something different, then it might be an important result. I don't think it will happen. Right? But you can try it. Right? So the final results are B1 equal to A3 equal to C2 equal to A2 equal to B3 equal to C1. 6 of the coefficients are equal. Then the next, there are 9 coefficients totally. Then the next set is B2 equal to A1 equal to C3. So that is what you will get. B2 equal to A1 equal to C3, that we have already got. Now we have got one more, right? I hope I haven't messed it up, but yeah, if you combine the two, what you get is A3 equal to A2. So the two sets of equalities can be further combined, and that's what probably I have written here. Yeah, you can establish, if you use this, the second transformation, you will probably get A2 equal to A3 or something like that, and so you will combine the two equalities into one. Right? So 6 of the coefficients are the same, 3 of the other coefficients are also the same. Now if I put this together, so what effectively in anticipation of the final form, Selin calls this to be lambda plus 2 mu, and this, I'm sorry, this he calls to be lambda, so this to be, you can call it anything, you just need two coefficients, two independent coefficients, right? There's no harm in taking this to be lambda and this to be lambda plus 2 mu. So this is how it is. So to match with what we normally associate with as a Stokes relation, right? So if I substitute that here, what will I get? Now D1 is going to be A1 D1. So A1 is lambda plus 2 mu D1 plus A2 D2, that would be lambda times D2 plus A3 D3. So that is again lambda plus D3 minus D. And similarly, D2 will become, right, lambda D1 plus, you can guess D, plus again lambda D3 minus D. And then D3 would be lambda D1 plus lambda D2 plus, you can call them any set of constants, certainly not lambda and lambda, not involving lambda and mu, and finally make it correspond to the expression we get, because lambda and mu are used as the coefficients of viscosity, right? So now if you look at this, so you see here that what I am getting, this D1, what it is lambda times D1 plus lambda times D2 plus lambda times D3, right? And D1 plus D2 plus D3 is simply the trace of the matrix in this representation. We have already shown that the trace of the matrix is invariant under transformation, right? So I can replace that simply by the divergence of the velocity field. So if you look at this, what form it will have in the diagonal representation, it's going to have the following form: E1, E3, right? Because this is a matrix. Finally, stress tensor is a matrix, but only in this coordinate system, it has a diagonal form. So finally, I have, so what I want is a tensorial relation. Generally, it's only in this coordinate system it has the simple form. So if I write it in the tensorial form, clearly I am going to get, I have a minus b plus lambda times the divergence of the velocity, which is the trace of d, minus b plus, right? So that is going to be a constant factor actually in each one of these equations. So that will obviously lead to the identity. If I want to write this in the matrix form, you can easily verify. I'm just writing, you just substitute all of this, you have it there, right? And you gather everything together and then finally writing it in a matrix form, that's all, right? So then this whole thing is plus 2 mu times d1, d2, d2. It's important to write it in this form because what I want, this is just a tool or a means to get to the final result, because what I want is the form in any representation, right? So by using this, now I can go back to the original representation and infer that the general form for linear is minus t plus in any representation. Even when d and d are not diagonal, it will have the same form. Again, I am using the second hypothesis of Stokes, that the form, the functional form that relates t to d is independent of the particular coordinate system you choose. So I transform everything to the diagonal representation because it's easier to prove the functional form and then go back and argue that this form should hold in general irrespective of the transformation by making use of the same hypothesis, right? So are there any questions on this somewhat long-winded? Yes. So that's what we wrote down one transformation, right? We got a set of equalities between the coefficients. You can use this transformation, you will get a few more. If you combine them together, and not done everything on the board, I want you to try it, including the proof of how that D and D will be diagonal in the same coordinate transformation. That also requires some manipulation like this, but as for that I want you to refer to second Aris. Yes?
In the second column, whenever is used, we just refer to as new projects again?
No, you can refer to it as anything you want, right? But I finally want it in the form in which the stress strain or the stress rate of strain relation is represented, and what we commonly understand as the viscosity is what it appears there. You call it whichever coefficient you want. Your viscosity then will not correspond to the viscosity the rest of the world calls viscosity. So you can be unique in that sense. There are many ways in which to be unique. I don't think this is a particularly profitable way. You have to be unique naturally. You cannot force yourself to be unique. Right? So there's no need to introduce additional. This is what the world calls a viscosity. So I'm just, with the hindsight, I know what to be. If you don't want, you can simply call this some alpha and some beta, and finally get to a certain form, and then say that if I want this to match with the commonly accepted form of the linear relation. The point is that there have to be two coefficients. What you call them, it depends on why for you have even 2 mu. Why not leave it at mu? Right? But if you put it as 2 mu, then what the equations will give is what finally will make mu the viscosity that is measurable by experiment. Right? That is the reason. It's open, you can just leave it as some coefficient. Alpha and beta is already introduced in the general form. You can call it any two, delta and whatever. Right? And leave it at that. If you want to make correspondence with what the convention is, then this is what will help you match with that. Right? This mu is finally what will turn out to be the viscosity that we all know as viscosity. Okay? Important thing to remember is whenever you ask, this is a far cry from the so-called Newton's law of viscosity. Whenever somebody is asked what is the Newton's law, then they write something like this. Right? And some people also argue that it has to be a negative sign because the fixed first law has a negative sign and the Fourier's first law has a negative sign. I think all these are, finally the relationship between, this is very limited, this is just a relation between a component of the stress tensor and a component of the deformation tensor. Some very special circumstances. This cannot be taken as anything representing the linearly viscous fluid that we have arrived. Right? Now we can make two further divisions, and when I say that it is incompressible, then it will become minus pi plus, whereas the compressible, the form will remain the same, but here you have to know that P is not an independent variable, but P is dependent or given by a local equation of state that relates P to the density and temperature. Now we will get, finally we are in a position to derive the so-called Navier-Stokes equation. And for that, I simply have to substitute this D. These are obtained for what we may generally call as a linearly viscous fluid. It can be, because the relationship between D and E is linear, so sometimes referred to as a linearly viscous fluid. So the most general form of the stress rate of strain relation can be, this may be referred to as a Stokesian fluid. These are some common terminology used in continuum mechanics. The linearly viscous often called a Newtonian fluid would be extremely charitable to Newton, because Newton did not think of the stress and the deformation in anything as general, even remotely close to this. So we use the conventional terminology, what is referred to as a Newtonian fluid may be regarded as this. Right? So now what I want is this, the final equation, because that's what I'm going to use to solve any given problem. So in T, now I have to substitute either of these two relations, but as it will turn out, if I work out the relations for the compressible fluid, I can easily get the equation for the incompressible fluid by simply making del dot P, or the divergence of the velocity, 0. Right? So if I am able to do it for the compressible fluid, I will easily specialize for the incompressible fluid. So now what T has is this form, minus T plus basically calculate both the divergence of this and the divergence of this. Right? So divergence of the first term is very easy to calculate. In general, if I have a tensor which is given by some scalar, let's call it alpha, right, times I. This alpha is not related to that alpha, but if we use alpha, then it's not really, that confusing to apply the same notation here. So I have some scalar multiplying a unit tensor. Now I want the divergence of that tensor, right? So to prove that, I can use a general relation, right? General relation for the ith component. The divergence of any tensor is AJI comma J, right? So this would be alpha delta Ji comma J. Simple, just blind application of the formula will often lead you to the correct answer. So now, delta J is just a constant, it's not going to be differentiated. The only differentiation is for alpha, which could depend, so the pressure J would be a function of position, right? And so is the divergence. The velocity is also a function of position. Lambda and mu are constant. So this would be alpha comma J. Delta Ji or delta Ij doesn't matter. This is simply alpha comma I. So the ith component of this is alpha comma I. So what can I write? So this is the ith component. What can I write for this? Generally, the full vector form. What is the gradient of alpha, right? Because alpha comma I is nothing but d alpha by dxi. This is nothing but the ith component of the gradient of a scalar alpha. Alpha is a scalar here because both p and the divergence of the velocity are both scalars. So I am just thinking this general, any alpha it can be. So I got this very useful relation. So whenever you see alpha times I, divergence is simply the gradient of that. So this will then give me, this part will give me, minus the gradient of p, right, plus lambda times the gradient of the divergence of the velocity vector v. If we run out of time, what is required is to calculate the divergence of the this, but here I am assuming the viscosity, right? There is a further complication. The viscosity is a constant, but it will be a function of the state, as we have said. That means it can in general be a function of rho as well as, for instance, temperature. Because we have not so far considered temperature. You have more general case where you have to solve the energy balance equation also with the temperature dependence. Normally viscosity, density dependence is often neglected. Temperature dependence might be significant. So temperature is a function of position. Then you would also have to take into account the gradient, I mean the divergence of that will also act on that, right? So since u is a constant here, but its function of the state can be function of density as well as temperature. Here I am assuming that mu is a constant to simplify. You know, really considering what is called as a constant. So see, here when I said mu is a constant, it meant that mu is not a function of the properties of the motion, the velocity and the velocity gradients, right? But it could be a function of the density and temperature. That is what I mean. Just as a pressure can be a function of density and temperature, right? So that is possible. But if you neglect that, then I can write is equal to, I can write it, only there I can write it, because otherwise, right, you have taken the divergence, which is a partial derivative with respect to the position. So if mu is the function either of rho or t or both, and both rho and t, incompressible fluid, again this won't come into the picture. Even for an incompressible fluid, viscosity is dependent on temperature, it might not always be possible to neglect that. Right? So if that is the case, and the temperature depends on the position, then I cannot take the mu out. So here I am assuming mu is absolutely constant, independent of the state of the fluid at that point. So then I can take this out. Then I am left with calculating this, right? This we have to calculate, we will do it next week.